right, can people in the back hear me now? All right, so let's get started. We'll start off with the usual, any questions from the last lecture? So if you remember, we were stuck in population genetics, if you will, or moving through population genetics, and I'm a little bit behind, but I'm hopeful we'll be able to catch up partly at least today. So what I want to do today is finish up my discussion of natural selection, and then talk about those other two evolutionary forces that we mentioned, or I mentioned, genetic drift and gene flow. All right. So just to remind you, we spoke about positive selection, or I spoke about positive selection, and that was beneficial mutations fixed. So this describes, this body of theory describes what happens when a new mutation is beneficial. That is, it confers a fitness advantage to the individual or individuals bearing it. Right? And the result is it increases in frequency. Right? That's all there is to it. Purifying selection is sort of the other side of the coin. Okay? This describes what happens to deleterious mutations. As you might expect, if a new mutation is deleterious, that is to say individuals that bear that mutation don't survive as well or don't leave as many offspring, that's what we mean by fitness, then natural selection tends to remove those mutations from the population. And when I was discussing purifying selection, I also talked about mutation, selection, balance. The question being, why then would you see deleterious mutations in the population if they're being removed by natural selection? Well, the answer is mutation is continually putting these deleterious mutations into the population. Right? There's active research on what fraction of new mutations are deleterious, how deleterious they are, and what fraction of mutations are beneficial. But the idea is, or the general understanding is that there's many more deleterious mutations out there. Right? That is to say, if you take something that's working fine, a protein, say, and you make a random change to it, usually you're going to break it. Right? Occasionally you make it better, but usually you're going to break it. And this is one of the problems a lot of people have with the idea of natural selection or evolution occurring under the influence of natural selection is there is this random component to it. Right? There's this random input of mutations that all have some fitness effect. Right? But remember, natural selection is a non-random force. It basically looks through all these mutations and removes those that are deleterious and brings to high frequency those that are beneficial. That's the non-random portion of this entire process. Yes, I can. I will too. All right, and then then we have balancing selection. We already touched on balancing selection when we talked about sickle cell anemia, so I'm not going to go into this in any more detail. But this is where the heterozygous individuals are the most fit. Now, see, if I were writing smaller, I could have gotten all in one line, but okay. So that's where the heterozygous individuals are most fit. Natural selection, in this case, acts to keep both mutations, both alleles in the population. Right? Both mutations being maintained in the population under balancing selection. Okay, so that's all I wanted to say about natural selection. I just wanted to finish that up. Now I want to move to a new topic, which is genetic drift. And if the question is, can I write more neatly, I can't, actually, so I'm sorry about that. So what is genetic drift? This is, so when we discussed, I'll back up a second, when we discussed Hardy-Weinberg equilibrium, I kept saying in very large populations, and sometimes I think I even dropped infinitely large populations. The theory for Hardy-Weinberg is that the frequencies we get are when the population size is infinite. And we all know that in real life populations can be big, but they're not infinite. Infinity is really, really big, right? And bigger than any population. So genetic drift is this random component in random changes in allele frequencies. Okay? And I'll illustrate that. Here, I'll illustrate it with a very simple experiment. We'll do it right here in front of you. Hopefully it will work out. There's a chance it won't, but eventually it will. So I'm going to imagine we have a current generation, which I'll call current gen. And we'll imagine we have 10 alleles in this population. So sometimes population geneticists, remember I talked about models and why models can be quite useful. Well, some models are so simplified, so abstract, that they just think about a population not as being individuals, but a bunch of alleles floating around in the population. So that's how we're going to think about it. We have 10 alleles in this population. I guess that would mean we have 5 diploid individuals, but just think about it being we have 10 alleles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's our 10 alleles. I'm going to label them. I'm going to label them 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? So I just decided to do the labeling starting with 0 instead of 1. The reason will become obvious in a second. And we're going to imagine that we have 2 different alleles. We have these white alleles. Here's one. Here's another. And we have these green alleles, it's chalkboard green, right? We have 8 of those. So the allele frequency in this the frequency of the white alleles in this population is what? 0.2, right? So let's get that. So the frequency of the white allele is, so I'll go like this. Frequency of the white allele is 0.2, and the frequency of course, the black or the chalkboard allele is 0.8. Okay, so what we're going to do is we're going to think about what happens in the next generation. And we're going to just let genetic drift be the only factor that's playing. So there's no natural selection, no migration, no mutation, just random genetic drift. And what we're going to do is we're going to sample 10 alleles into the next generation. Let me count for a second. I can't talk and count at the same time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we need to randomly sample. What we're going to do is we're going to randomly sample alleles from this generation and put them into this one. Now, of course, if we just took every one of these alleles and put it in the next generation, the frequencies would be the same. What we're going to do is we're going to randomly sample them with replacement. So then the question becomes, how do we randomly sample alleles? Well, you need to have some way of generating random numbers. And I just happened to dig into my closet and I've got some random number generators. All right, so these are dice, and most people in this class probably think, well, dice have 6 sides. Well, not all dice have 6 sides. These have 10 sides on them, 10 faces, and the faces are labeled 0 to 9, 0, 1, 2, 3. There's, probably, what fraction? Just raise your hand if you know where these dice came from. All right, so there's a handful of people that had a high school social life as miserable as mine, but both of you evidently did okay. So what I'm going to do is I'm going to roll this die, and we're going to select each allele in the next population. So I rolled a 1, so that means that this guy gets the label 1. That is to say I copied a white allele in the next generation. So I'm going to do this again. I got an 8. Here, somebody else needs to help me. Who wants to, in the front row wants to roll a die with me? It's exciting. Okay, well, it's not, I mean, it's exciting if you're, I get excited, it's pretty lame. What do you get? 6. Roll again, we need to keep going. 4 for me. 9, 6, 9 again, 4 from you, 0 for you, 0. All right, so it actually did work. So let's figure out which one of these are white and which are chalkboard. So these last 2 are white. It's magic. The frequency's changed. So you will all agree that the frequency of the white alleles is now 0.3? Yes. Maybe. Yeah, I don't know. I've got other dice too, so I've got 20-sided and 12-sided and 8-sided and 4-sided too. But, all right, so I played first edition, by the way, so none of this will be. So anyways, the point here is that the allele frequency's changed, right? And this is an illustration of genetic drift. This is remember, I told you about 4 forces that cause allele frequencies to change. One of them I said was genetic drift. This is just random chance, right? This is sort of the bus hitting somebody type of events in life, right? It turns out that under the influence of genetic drift, over time, so if we were to repeat this experiment into the future, let's just say we said, okay, this is generation 1, this is generation 2, 3, 4, and so forth, and we're to continually roll dice. First of all, this would qualify as probably the most boring lecture in history, right? But secondly, eventually one of these 2 alleles would win. That's to say, eventually one of these 2 alleles would become fixed. And once the frequency hits 0 or 1, then of course, in the absence of anything else, the frequencies will stay 0 and 1 forever after, right? Until a mutation occurs, that would be the only thing that could change the frequencies after that, right? Is that clear? And I should say another thing too. I'm just going to tell you the results. With genetic drift, you can actually calculate the probability that the white allele eventually wins and the probability that the green allele eventually wins. So if we were looking at it right now and say, okay, we're going to do this experiment. It's going to be tedious and long, where we do the sampling over and over and over again. But what's the probability that when one of these 2 alleles finally becomes fixed, that it's a white allele? Or what's the probability when one of these 2 alleles becomes fixed, that it's a green allele? Well, at this point, the probability that the white allele becomes fixed is its frequency in the population, 0.2. And the probability that the green allele becomes fixed is 0.8. Right now, if we say conditioned on actually seeing the population at this point, where we now have 3 alleles, those probabilities change, right? But from this point on, if we were to say, eventually, what's the probability the white allele becomes fixed? 20%, 0.2. Okay. What does that mean for a new mutation? So we talked about beneficial mutations, deleterious mutations is the third kind, which fits right between them. They're called neutral. These are mutations that have no effect on the fitness of the individual, right? No beneficial or deleterious effect. So let's imagine we have a new neutral mutation occurring. What's its initial frequency in the population? No, it's not 0. It's new. It just is there. There's 1 copy of it, and there's 2n individuals in the population, right? So its initial frequency for this new neutral mutation is 1 over 2n. What's its probability of eventually becoming fixed? 1 over 2n, right? I said that the probability that an allele becomes fixed is its frequency at that time, right? So its frequency when it occurs is 1 over 2n. So most neutral mutations, of course, are going to be eventually lost, but occasionally you're going to have one that wins. That is to say, that replaces all the other alleles in the population, even though it doesn't have any fitness advantage. That's genetic drift. Okay? So just random chance. And just remember too that when we're doing this sampling procedure, it's not like I said, well, these white alleles are a little bit better, so we'll make certain that they have a higher probability of being placed into the next generation. No, every one of these alleles had exactly the same chance of being sampled into the next generation. So it's not as if it's the case that one of these alleles conferred a fitness advantage over the other. They all have equal chance. So this is new. There's no natural selection. No games. This is an honest 1-generation genetic drift simulation. You can keep the die if you want. You can get them at games at Berkeley on Center and Check. All right. So that's the first thing I want to say about genetic drift. What is genetic drift? There's a couple places where you actually, a couple terms you'll hear sometimes in the literature, which basically is genetic drift. One is bottleneck. Bottleneck effect. Okay? And so what I'm going to do to illustrate this is just make a graph. We'll have time on one axis, and then we'll have population size on another. And the way we'll sort of illustrate population size is sort of the width of a column. So the population size will be something like that at this point. A bottleneck is when you have a dramatic decrease in the population size, followed by an increase later in the population size. So here we have a population that in the past was abundant. There were a lot of individuals. Then went through this period of time during which there were very few individuals in the population, followed by an expansion. Okay? Now, this is another important point I want to make about genetic drift is the fluctuations that you will see in allele frequencies are greater when the population size is small, right? So if you have a very, very large population containing millions of individuals, the allele frequencies will fluctuate, but they'll fluctuate in terms of the frequencies by a very small amount, right? If you have a very small population, you can get much more dramatic swings in the allele frequency. So one way of expressing that is to say that genetic drift is more powerful in small populations. Okay, it's more powerful in small populations. So what happens during this bottleneck effect time, during this bottleneck, here's the bottleneck, by the way, is that genetic drift will be stronger during this period, and you will lose genetic variation, right? Because genetic drift is more powerful, so these alleles won't take as long to become fixed or lost in the population. Okay? So during this bottleneck period, the effect is actually for the population to lose genetic variation. And if you're a conservation biologist, where we think a lot of species right now are in this phase of their history, that's a problem, right? Because if you don't have genetic variation, remember natural selection works on raw genetic variation. If there's no variation in the population, you can have all the selection in the world and you won't get a response to it, right? So you have to have genetic variation on which natural selection can operate to get evolution under natural selection. So there are examples. Cheetahs are an example of a species that we think has a population history like this. Cheetahs are so similar one to another genetically that they're I think they're the only mammal that I've heard of where you can actually do skin grafts from one cheetah to the next, and the cheetahs won't reject the skin grafts. So that's how genetically similar cheetahs are. And the idea is that cheetahs have gone through a fairly recent bottleneck where they lost a lot of their genetic variation that probably existed at one time. Another manifestation of genetic drift is called the founder effect. And the idea here is we have a population. Here's a population where the population's a big one, okay? And some individual, or maybe a small number of individuals, founds a new population. Okay? Now, if this number of individuals that samples or founds this new generation is small, as I have in this example, then you can think about its composition genetically being a random sample from this population here. Right? So going back to our white and chalkboard colored alleles, if it's one individual that just happens to be a white allele, right, you can have a low frequency of the white allele here and a very high found frequency of the white allele over here. Right? So just by chance, you can have a much higher frequency of an allele here than you see here. And there's lots of examples, especially in human genetics, of what we think is the founder effect, where you find small isolated populations with, say, a high incidence of a particular disease. And the example I gave in my notes involves Huntington's disease. So Huntington's disease is an absolutely horrible or neurodegenerative disorder. Strikes people from the mid-30s to about my age, the mid-40s. Okay? And basically deteriorate very rapidly and results in death. Okay? They know what the gene that is responsible for Huntington's disease is. It's called HD. It's called Huntington. There's a particular gene that's defective. It's one gene that's defective. And it's actually caused by a repeat. So you have the CAG repeat. And basically, if the repeat gets too long, people will have Huntington's. And if it's of a normal shorter length, then you don't. Right? So population geneticists call this type of repeated elements in the genome they call microsatellites. It's not important, you know it. But basically, people call this kind of a microsatellite disease. It's caused by having too many repeats of CAG in this Huntington gene. Okay? Well, so why am I telling you this? There's a population in Venezuela, Venezuela, where Huntington's disease is at a very high frequency. And they think it's because of the founder effect. The town was founded quite a while ago by somebody who just happened to have have this long CAG repeat, or at least one of the individuals or several individuals have that long CAG repeat. So the disease is at high frequency in this town. Just one example of genetic drift. Okay, so what I'm going to do next, before I get to gene flow, is bring the screen down, unblank the screen. So I want to illustrate. So one of the problems with population genetics is, like, frankly, the little population genetic simulation we did was kind of silly, lame. We were only able to go one generation. But on a computer, you can sample many more generations. So I wrote a little computer program that illustrates this. I mean, this has been a bad day for your perception of me, I suppose. But I like doing this stuff. So what can I say? So it's a program I wrote. It's, if you're interested, it's a little Mac program. I don't know how many of you guys have programmed on the Mac, but it's actually quite a bit of fun. I've used Cocoa and Objective-C. What I'm showing you here is a little graph with time along the x-axis and the frequency of the big A allele along the y. And as far as this stuff down here is concerned, you don't really have to worry about that, right? Don't worry about that. But I have to have, these are the mathematical model. Mathematical models have parameters. These are the parameters I put in here so I could change them and illustrate different things. Okay. So first of all, let's do have infinite-sized populations, and let's start with the frequency of the big A alleles being 50%, and let's have no selection. Right. So this is the Hardy-Weinberg case. What do we say happens to the allele frequencies? Well, nothing. Right. When you don't have selection, you have infinitely large populations. Hardy-Weinberg says allele frequencies don't change, and there you have it. Right. So the computer program is just doing the Hardy-Weinberg equations I showed you over and over and over again. Let's bring the frequency down to a small number, make it 0.02, say, and let's make individuals with have a selective advantage. So now what we're doing is we're illustrating natural selection. So this is natural selection where individuals having big A are unambiguously better. Okay, this is the example I gave you, where big A people are the best, or individuals are the best. Heterozygous individuals are intermediate in fitness, and the individuals that are homozygous for the little allele there kind of have the standard fitness. So this is big A is a beneficial mutation, and you can see that natural selection increases its frequency until eventually the allele becomes fixed. Okay? That's just natural selection, but that's natural selection with no genetic drift. Okay? Let's look what happens when we have a finite population. That is to say, let's see, how many individuals do we want? We have 10,000 individuals. And so this is what happens when we have 10,000 individuals and the allele starts at a frequency of 0.02. Okay, you can see that the curve is more or less what we had with the infinite case, where the infinite case was a very smooth curve. Here you can see a few number of wiggles. Those wiggles are caused by genetic drift. Now, what's the problem with this simulation? What's the starting frequency of a new beneficial allele? It's just 1/2n. So the initial frequency is one copy. So what I'm going to do is I'm going to start this with, instead of 400 individuals, one individual, and see what happens. It was lost. So here we have a beneficial mutation. And this beneficial mutation has a very strong effect on the fitness. A 10% fitness advantage is a huge fitness advantage. And yet it was lost in the population. Here it's lost again. Every time I push it, the button, there, oh, shoot, I missed it. Okay, there, okay. So you notice I had to push the button. Every time I push the button, we have a new realization of the process from new starting conditions with 1/2n. Most of the time, the beneficial mutation was lost. About 20% of the time in this case, you would find that, that the beneficial mutation is fixed. Okay, so this is kind of the example of, like, some Olympic athlete crossing the street and getting hit by a bus, right? Somebody's, well, maybe not the best example. It depends on whether Olympians are actually, have a higher fitness effect in terms of reproduction and survivability. But it's an example of an individual bearing this great mutation being hit by a bus type of thing, random chance. Okay, so that is the effect of natural selection and genetic drift combined. Let's make the population size a bit smaller so we can see what happens to those wiggles. You can see when the population size is smaller, the wiggles, 1, 2, 3, 4, 5, 6, there. The wiggles are bigger, right? We can start this. Let's get rid of natural selection again. Let's get the frequencies at 0.5. And let's see what happens to these frequencies. You can see that is genetic drift where we don't have any natural selection going on. We started the allele at a frequency of 0.5, and you can see the frequency just like jiggers around, right? You can see here in this particular simulation, the allele is almost lost. It started off at 50%, is drifting up to a high frequency. The big A allele almost won, the little A allele was on its way out, almost out, and then the little A allele started to gain in frequency again. So eventually, I'm only showing this simulation over 1,000 generations. Eventually, one of those two alleles will win, with probability 1. One of those two will win. On average, it's taken much more than 1,000 generations for that to occur. See if we can get one to die out before 1,000 generations. I love this type of stuff. Oh, that one. Oh, did that die out? Oh, yeah. Allele A lost in 598 generations. So that would be an example of one of the alleles was lost within 1,000 generations. Let me illustrate balancing selection. I need to make that negative 0.5. Make that 0.1. Good. So this is balancing selection. This is the case where, if you look over here, the heterozygous individuals have the highest fitness. See, I haven't put these little mouse overs in. And the other two homozygous genotypes have lower fitness. What happens? So you can see that the allele frequencies seem to be hovering around, well, 0.75, it looks like to me, right? But you can see that you have genetic drift occurring because the population sizes are finite, and so the allele frequencies are jittering around a bit, but they're not really fluctuating as widely as they did before. Every time I run the simulation, they seem to want to hover around this point right here, right? It's not like before when we did the genetic drift simulations, the allele frequencies went all over the place, but here they sort of are hovering somewhere around 0.6 to 0.8 in their frequency, somewhere in there. Every single time I push the button, we get a different realization. This is balancing selection. This is the sickle cell anemia scenario. Okay? All right. I don't think there's anything else I can illustrate, but I thought this would be a useful little demonstration just so you can see what happens in these real simulations. It's difficult sometimes to illustrate the combined effect of natural selection, genetic drift, and so forth, right? So this is at least showing the combined effect of natural selection and genetic drift. We could also throw mutation in as well. Okay. All right, so that's that. Let's see. I think I'll use this board over here since I'm going to be using the screen in a bit. Free food. Okay. There's one last thing I want to say about genetic drift now that I remember it, and that's the molecular clock.